All right, well, welcome back. As promised, more work with this magnetic dipole. The statement reads, find the exact magnetic field a distance z above the center of a square loop of the side length w carrying a current I. Verify that it reduces to the field of a dipole with the appropriate dipole moment when z is much, much greater than w. All right, let's draw it out. We see here that we have a square loop. Again, we had a question like this earlier in the chapter, 5.8, I think. But nonetheless, when we draw it out, we see what we have. Splitting the lengths in half, w over 2, as we see. We have different angles for different measures. Theta goes to the corner, which is how we derive the line segment field. And then phi goes from the center to the center of the line itself. All right, so let's move forward. Same thing as last time. We need to know what the magnetic dipole moment is and the multipole expansion approximation for the field is. All right, so again, this multipole expansion is just a dipole term. I should clarify that better. So the solution, we will start with understanding that, again, we can manipulate the old situation with the new situation. We already found the magnetic field of a line segment, so we can modify that. Noticing that the square loop is just 4 line segments put together, we can multiply by 4, and based on this geometry, we can see what sine of theta 2 and sine of theta 1 are, given that theta 2 is equal to negative theta 1. Again, this was kind of described in more detail in an earlier problem. But nonetheless, for this particular setup for the line field, S has to go to the square root of z squared plus w over 2 squared. Again, that's just a Pythagorean thing. And then we know that since sine, in geometric terms, sine is the opposite leg over the hypotenuse. So you see here why we have the sine as defined as w over 2 all over the square root of z squared plus w squared over 2. Just use your geometry, let the instinct guide you, and so forth. So putting these modifications back together into the B field of the square, we see that we have 4 times the line segment, where we substituted in the negative sine theta 1 for sine theta 2. Those combine to give us 2. We can take that 2, we can take that sine theta 2 and the S, plug in their modifications and definitions, and then we see that the 2 on the sine theta 2 cancels with the 1 over 2 in the numerator of that fraction. And then we see that we can combine this through to where we end up with mu naught I over pi times w over the 2 square roots. Kind of nasty looking. So with the interest of the vertical component, so we can compare to z much, much greater than w, we have to multiply by another factor of sine phi, which is defined as w over 2 over square root of z squared plus w over 2 squared. Again, we got that from the specific geometry, not the angular geometry to the corner, like the sine of thetas were. Okay, fair enough. So we plug all that in. We see that we get mu naught I over 2 pi, where that 2 for the 2 pi comes from the fraction in the sine phi in the numerator. And then we get w squared over z squared plus w over 2 squared, again, because we have 2 of the radicals, and then times the square root of z squared plus w squared over 2 in the z-hat direction, because we want it vertical only. All right, so now for z much, much greater than w, we see that the denominator reduces to z squared and the square root of z squared, because the w over 2 term squared and w squared over 2 just vanish in comparison. So then we see that the square root of z squared is a z, or absolute value z if you really want to be technical. And therefore we end up with mu naught I w squared over 2 pi z cubed in the z-hat direction. Now we know that the dipole moment is m equal IA. What is the vector area of a square but w squared? So that makes sense. So for points that lie on the z-axis, where r goes to z, r hat goes to z hat, theta equals 0, blah, 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 we see that the approximation of the dipole field approximation works out, given that cosine of 0 goes to 1, sine of 0 goes to 0, and r goes to z. We see that it all cancels just like before, and we're good to go. What this highlights is clearly you see how the utility of the dipole term or dipole moment term works out here. We did 2 lines of work versus having to use all that geometry. So this approximation works really well from a large distance. Just to understand the context and how these tools can help you. And yeah, that's all for this one. Thank you.